Hello and welcome to Module 2.1, State Space Representations. Let's start with defining what we mean with a state space representation. And the extensive definition is this one. A state space representation is, first of all, a mathematical model. Typically, but not always, it's a mathematical model of a physical system, but it might be something that is more esoteric of a physical system. It might be something that is a model of the psychology of the person. Anyway, this representation is a mathematical model that is composed by a finite set of inputs, outputs, and state variables, that they are related by first-order differential equations, and they satisfy the separation principle. It's a long definition. Let's see what it means. First of all, the ingredients are inputs, outputs, and state variables. We will see what it means. Second ingredient is that all those quantities have to be connected through first-order differential equations. Moreover, there's this separation principle that states this, and we will see what it means physically. Separation principle means that the current value of the states contains all the information that is necessary to forecast the future of the output and of the states, given the inputs. Now we see. Notice also that there's something that is important. In our course we consider finite sets of states. It will be a little bit clear. It will be clearer later on why we consider finite states. Anyway, this finiteness is important. Let's see what separation principle means through some facts. First of all, we say that there's states, there's inputs, and there's outputs. Those ones will be physical quantities, signals, okay? So we've got some inputs, some outputs, and some states. And there will be some signals. The separation principle says that, first of all, the future output, so let's say that we are at time here right now, and let's make maybe things with different colors so it's a little bit more interesting. So inputs in blue, states in this color here, and outputs in this color here. Very bad. Green. Okay, let's make this, let's make this, and let's make, what was it, this color here, states. The separation principle says, first of all, that the future output depends only on the current state and the future input. So the future output, that is this green here, the future output, this stuff here, depends only on the current state, so the past I don't care, and the future inputs. I chose very bad colors. Somehow, the first thing that you've got to realize is that, first of all, whenever we have state space representations, if I am here, now is here, if now is here, knowing the state and knowing the future inputs allow me to predict the future output, since the future output depends only on the current state and the future input. If you see, somehow, from a graphical perspective, to forecast this output here, I just need to have the state here and the input here. Second thing, the future output depends on the past input only through the current state. If we redo the situation, the figure as before, so we have the output, we have now, okay, the future output here depends on the past input, let's say that this is the past input, only through the state here. So basically, the state right now somehow condenses all the information about the past input. Last thing that basically is a consequence It means that the state, what it's doing, is actually acting as a memory for the system. It summarizes the effects of the past inputs on the future output. So somehow this separation principle says that if this is time, if this is now, having the state, the knowledge of the state now, somehow separates the output from the input. And let's say that this is the output. Because this state here right now condenses everything that I know from before. Let's say an example. Maybe an example will be a little bit more clear. And let's retake the blue. Now let's take a fire, it's a little bit more pretty. A flashlight that is rechargeable. Okay, so we have this flashlight. It makes a little bit of light. And the state of the flashlight, assuming that the output is how much light the device is producing, the state of the flashlight is the level of charge of the battery and the on-off button, of course, because if it is off, it doesn't produce. Why the level of charge of the battery is the state of the system? It's the state of the system because independently of the, let's say that this is time, and let's say that this is how the charge, the start of charge of the battery was evolving in the past. If the battery right now has this level of tension here, okay, the light that will be emitted by the flashlight will be basically something that depends only on this state, doesn't depend on the past state. If you see, this level of charge works as a state for the system because it separates what was happening in the past with what will happen in the future. Somehow, the state of the system, the level of charge, summarizes all the past history. This is actually in first approximation because in a true flashlight somehow also the rate of discharge matters, but in first approximation somehow just the level of charge is enough to understand what will happen in the future. To understand what happens in the future, you not just need the current state, not the past things. Let's see from a notational point of view what we use as a notation. U will be our inputs. Always U inputs. It comes from Russian, so basically it's not E as an input but U as an input, because I as an input, U as an input, because Russians were using U as an input. The same for the outputs. The outputs will be the letter Y. The states we will always use the letter X. So whenever you will see later on U, Y and X, you will immediately understand what we are talking about. This will be an input, this will be an output, and this will be a state. Moreover, since we might have multidimensional systems with several inputs, several outputs, and several states, we need a subscript. M for the inputs, P for the outputs, N for the states. Always. This is something that everybody uses, and you must use this stuff here, this notation here. Let's see how to represent state space systems in continuous time. We say that we need to have a finite set of first order differential equations. Remember, typically the output is connected, but this is a notation that we use here, and you will see later on some examples where we do not use this notation perfectly. The outputs will be static maps from the states and the inputs. The states instead will be dynamic maps of the states themselves and the inputs. Notice that from a structural point of view, we have n inputs, n states, p outputs, m inputs. From a structural perspective also, we have that the states will be updated only through the states and the inputs, and not the outputs. See that somehow the outputs doesn't go affecting the input in this way, the state in this way. Moreover, for how we write it that somehow the outputs are just functions of the inputs and the states. This is so to separate, having this separation principle. Okay. Of course, using this notation is a little bit inconvenient because it's a very long notation. So we will often use an abbreviated notation where we use capital letters or bold fonts. This x here will correspond to this vector here. This y here will correspond to this vector here. U, of course, will correspond to this vector here. And f, whenever we write this, we are indicating this stuff here. The same for j. We are indicating this stuff here. It's a little bit more convenient. So, whenever you will see a bold font, you've got to immediately know that we are talking about different states or different inputs, different outputs, different whatever. Names, very important. This is the state transition map. Why? Because you transition the state from a certain x to another one. And this is called the output map because somehow it associates to the state and the input, the output. So, names. Remember to use them because it's important. In discrete time, we do not have first order differential equations, but we have first order difference equations, where the future state is basically a combination of inputs and previous states. The same structure as before is holding here, in the sense that we have, first of all, n inputs, n states, m inputs, and p outputs. Moreover, the state is propagated through just considering the past states and the inputs. We are not having the output inside here. Okay. The same applies here in the status here. Of course, as something that mimics as before we were having x dot equal to f something. Now in discrete time we have x k plus 1 equals to something depending on k. Notice that we will use often k as the index for indicating time, discrete time. So whenever we see k, you've got to immediately understand that we are talking about discrete time. Sometimes we might be sloppy and use also t, but t preferentially we use it for continuous time, indicating continuous time. As before, we are having a compressed notation where we have a situation like this one. Of course, these will indicate this vector here. These will indicate this matrix here, etc., etc. Okay, so we saw something that is x dot equal to f of x u and y equals to g of x u, and then we might have another alternative version here. How do we go from this situation to this situation here? We will see in the next lessons. It's something that you have to do. It's called discretization. Notice that whenever we talk about systems and we want to describe a system in terms of state space representation, very often we do it directly in terms of continuous time representations. Why? Physical laws are differential equations. The force that is equal to mass times acceleration, this is something that is defined in continuous time. So whenever we use physics tend to lead us in this way to this stuff here. Of course, since we are doing digital control, we will not be able to use this stuff here for doing control. We want to have something that is discrete. So there will be the need for moving from this representation to the discrete one. So I hope that you see the flux. The flux is basically that we start from physics saying some function, some laws in continuous time. This might not be written in a state space form, as we will see very soon. Then we write it in state space form in continuous time, and then we discretize it. Little by little, we will do all of those steps, but at least from the beginning you get a little bit of the picture. Very important thing. We are talking about generic functions here, but are generic f's and g's valid, remember what are the requirements for a state space representation. From an intuitive point of view, if we write something like this, shall we pose some assumptions on the structure of f and g? Yes or no? Yes, even if we didn't see it up to now. What is the problem? Sorry. Of course, I did a stupid thing that is like to do not read the question, but anyway, it's okay. I will fix in the website. We can't use any type of f on g for writing state space representations, because we must guarantee that there exists a solution and it's unique. Somehow, if you see it in this perspective, we've got time, we've got a certain initial condition x0, okay, let's say that we've got only one state, and let's say that we also have a certain input that is defined in time, okay, this is our input in the time. Whenever we write a system like this, we would like the system to be well defined, in the sense that we would like the x to exist and be unique, at least up to a certain time horizon. If, mathematically speaking, we are not able to guarantee that there exists a solution, then we are writing something that is useless from a practical point of view. For being useful from a practical point of view, those objects here must return something that we can use. If we write something that for which the solution do not exist, then we basically waste some time. So the condition is that whenever we write state space representations, f and g must be good enough for guaranteeing what? Guaranteeing that there exists a solution for at least a certain horizon, and this solution is unique. This stuff here is something that you should have done in a functional analysis. Anyway, if you don't remember the conditions, you should Google for this stuff here. A simple criterion for that guarantees a simple sufficient condition that guarantees the existence and unicity of the solution for state space representation is that both f and g are Lipschitz continuous functions. That means that basically the first derivatives are bounded. Let's see an example of a state space representation that is an important example because it has got some characteristics that we will recall quite often. X dot equal to minus x squared, y equals to x. See that here there's no u. Okay, it's an autonomous system in the sense that there's no input here. Let's say also that we have this system here. It's a nonlinear system, of course. You see that there's some nonlinearity here, but we will talk about nonlinearities better on if you do not know what is nonlinear, you will know very soon. Anyway, we have a certain system and we start from a certain initial condition. And then the solution is this one. That means what? That means that if we are starting at time 0 and we are starting, maybe it's better if I draw in this way, we are starting at time 0 from minus 1, then the solution for x of t, and this is t, the solution for x of t is 1 over t minus 1. That means what? Something that goes to minus infinity as t approaches 1. You see it? What does it mean? It means that for t that reaches this time here, we've got a finite escape time. Basically, the system explodes. We start from a certain finite value, and in a finite time, we go to infinity. Minus infinity in this case. This is an important thing that helps realizing that whenever we have a system, even if we have a very well defined initial condition, we might do not have the solution defined over the whole R plus usually. We might have that after at a certain point the solution explodes. So it might be that x of t exists only between, let's say, 0 and a certain time. But notice that the solution here is unique. So this is a well-defined state space representation. Another important question: can every physical system be described with a state space representation? Remember the definition that we gave in the first slides. If you don't remember, go back, check, and then answer this question. Can we describe everything with state space representations? Yes or no? No. The answer, of course, is no, because we might have systems for which we have, maybe it's better if I do this, for which we have an infinite number of states. For example, if we are having a bar of metal and we consider the temperature of this bar metal, the temperature is defined everywhere. And somehow every point in the bar influences the other neighboring points. We have some situations for which we have PDEs, partial differential equations, for which somehow the parameters of the models are distributed. They are not lumped together. In the case of the bar, what happens? It happens that we have a parameter defining the temperature of the bar everywhere. Since we've got everywhere, we've got an infinite number of states, and our state space representation would become infinite dimensional. And this is something that is not valid in our cases, because how do we handle an infinite dimensional system in a finite dimensional computer if we want to do control? So whenever we have PDEs do not lead to state space representations. What is the situation that, what is the solution of we engineers whenever we find something like this? Well, one of the potential solutions is to define a grid over the bar and say that instead of considering an infinite amount of points, we consider only a finite number of points, and we do this finite elements analysis. Another important case for which we can't write the system in a state space representation is whenever we have continuous time systems where there are some delays. This is a important and delicate topic, so we will discuss about this a little bit better later on. The problem is that, just as an anticipation, but we will understand it better later on, delays should be modeled with an infinite number of states. And this is not good for us because we want something that is a finite representation of the system. Okay, then let's make an example. Make me a little bit more interesting example with respect to before. Dynamics of sugar and insulin in concentrations in blood. So we define two states, that is the sugar and insulin concentration. We define two inputs, that is how much food you are eating and how much insulin you are taking. And also there's a parameter. Let's assume that y is equal to x in this case, so that we ignore some of the outputs. Let's assume that we have only inputs and states. Let's also consider this important parameter here, that is the sugar concentration in fasting. Let's say that you haven't been eating for 2 days. If you haven't been eating for 2 days and you have been doing anything for 2 days, you would have kind of a certain equilibrium of the system. We will define equilibria better later on, but let's say that what would happen to your body in case you were not eating for a lot of time, for now. And let's say that this is just a parameter that helps us defining the state space model in a good way. The first part of the state space model is something that looks like this one. Notice that we have still a first order differential equation that connects one state to the other states and the inputs. Notice that here we are describing only what happens to one state, that is the insulin concentration, and we are describing it through a condition. And graphically, this equation here looks like this. Let's pretend that all those parameters here are 1, just to simplify the situation. Let's assume that we are looking at this situation here, x1 bigger than c. We have time, then we have this parameter c, that let's draw it in green. That is, let's say, what would happen to you if you were fasting and not eating for a lot of time. Then, in case x1 is bigger than c, okay, let's assume that x1, let's say that x1 at time 0 it's here. In case x1 is bigger than c, then what happens to the derivative of x2? x2, what happens? x2 is, first of all, increasing thanks to this term here, because x1 is bigger than c, and this means that this positive here is a quantity. So it means that the time derivative, that is the slope of x2 at time 0, okay, it's first of all something that is positive, and the more positive, depending, the more this distance is, the more this is positive. Then there's something that is a decay ratio. If x2, let's make it here, if x2 is here, then this decay ratio here is this big, okay. If instead x2 is here, this decay ratio is very big. This is basically a decay ratio that depends on if you are high, you go slower faster. If you're low, you go slower, you go to 0 slower. And then what happens also? You've got a food intake. And with the food intake, the more food you are eating, the more somehow you're ramping up. So, totally, let's say that with x2, let's say that with x2, let's say that this is x1, this is c, and let's say that this is c, x2, and then we've got also the food intake that is something like this. Okay. x2, what happens? There's a decay ratio that depends on how big it is. Then there's an increase ratio that depends on how big this is. Okay. And then there's an increase ratio that depends on how much food we are taking. Somehow this contribution, the sum of those three contributions here, decide how this derivative looks like. So somehow this model here says how, starting from x1, x2, and u2, you know how the derivative looks like, and you know how the evolution will be. Something similar happens whenever x1 is smaller than c, just that the state is a little bit different. Somehow, in this case, the insulin would behave in a different way. But somehow, the important thing is that you realize is that we have a state space representation, in the sense that we are connecting the first derivative of the state with the previous states, the other states, not the previous states, the other states, and the inputs. What was, notice that very important here is this separation principle. What was happening before doesn't play a role. Everything is summarized in the current state and the current input, and to forecast what is going to happen to the future states, we just need to know the future input, the future input, that is this one. This separation principle. Something similar, we can write something similar also for x1. Those equations here have got some physical interpretation, and I suggest you to think a little bit at what they mean from a physical perspective, and think about the biological interpretation of this thing. Anyway, Something that I think that you should do as a homework, and homeworks means that is something that you do if you want, but I strongly suggest you to do. Try to combine the various equations into just one by means of a certain additional function, that is this function here, so that we eventually get something that is like this. Why? Because this is the way that we use, this is the notation that we use in our systems. Whenever we design our controllers, we write the equations in this way here, because it's easier to process one equation. These kind of things with the case is not good, it's not useful, it's not nice to see somehow, and it's not nice to work with. So, since often it might be that with physics you write down this stuff here, it's also good to know how to go from physics to descriptions that are useful for a control perspective by means of some simple mathematical manipulations. Okay, notice that in all the cases before, I was forgetting to put the time. We might have that the state depends also, the state update rule depends also on time. For example, a rocket. Whenever we got a rocket, okay, we got a rocket that is launched, and as it's flying, it's consuming a little bit of fuel. Since it consumes the fuel, the mass of the rocket changes. Since the mass changes, the equations of the motion change. So this F somehow change. In the previous, for the rocket case, we should write things in a way that explicit X. In other systems, instead, this dependency on time doesn't exist. For example, for our Segway case, in the Segway case, the physical laws do not change with t, because the physical parameters defining the Segway do not change with t. So in this case, we have an time invariant system. This is time variant, of course, because time varying, because it's the mass changes. This is time invariant because time doesn't play a role. Of course, if the time doesn't play a role, we don't write it. Same thing of the same consideration that we just made for the continuous time happens also in discrete time. Last thing, very important thing. What happens if we do not have a first order representation? What happens if we've got something that looks like this? We say that we want something that is x equal to f of x u, y equals to g of x u. And if we have something like this, how can we write down our state space representation on top of which we will design the controller? Notice that often we will find from physics these type of representations. Well, there's a very simple trick that is to perform a change of variables. That means we take the stuff inside here and we call this x1, this x2. Sorry, let's make it a little bit better. This is x1, this is x2, this is x3, this is u1, this is u2, this is u3, okay, u3. And then we write down something that looks like this. In which sense? In the sense that, first of all, we know that y3 will be equal to this stuff here. y3 will be equal, of course, 3 dots will be equal to phi of x1, x2, x3, u1, u2, u3. This is x, this is u, and so you see it directly, okay. Then what do we have? We have that y2 dot, okay, what is equal to? It's equal to y2 dot, it is equal to x1. But if we have x that is equal to x1, x2, x3, Then what does it mean? It means that y2 is equal to 1, 0, 0 times this vector. Same thing we can do it for y dot. Y dot is equal to x2. It means that y dot is equal to 0, 1, 0, x1, x2, x3. Okay? And this way, what do? We are writing everything as the notation that we would like. If it is not clear, let's make us an example that is a little bit maybe more informative. Here we have y2 dot that is equal to minus 2y dot plus 3y plus minus 3y plus 4u2 dot plus 5u dot plus 6u. Let's write it as y2 dot is equal to minus 2x1 minus 3x2 plus 4u1 plus 5u2 plus 6u3. Okay? Now, y2 dot is equal to what? Y dot dot. Y dot is equal to x1. So y2 dot is equal to x1 dot. And this is equal to what? This is equal to, for sure, this stuff here. And this stuff here, let's call it a phi of x u. Then what do we have? We have x2 dot that is equal to what? X2 dot, where is x2 dot is equal to y dot that is equal to x1. And at this point, what do we have? We have the system that is equal directly written as we wanted, because this is capital X dot and this is our capital F of capital X, that is X actually. So, you understand what I'm writing? Okay. So you see, it's very simple. Try to redo it by yourself. It's a simple operation. In any case, from this, just a little bit of fantasy and trying to rename things in a correct way, you get it immediately. With this, that's all for this module, and bye. See you soon.